In Chapter 10, we will be looking at structure determination, and there's different ways we can determine structure using spectrometry. So we're going to be looking in this chapter specifically at infrared and mass spectrometry. The crystal structure that we have shown here is the sex hormone binding globulin, a protein called human sex hormone binding globulin, and this can bind prednisone. Structures here we can see where prednisone is bound. So these are anabolic steroids that can be taken by athletes, which can then get transported to their target tissues in the body, and it binds in this protein. So crystal structures are one way to see how they bind into the proteins and how they can get used by our biological systems. And what we can do to determine the structure so we know what prednisone looks like is use spectral information. There's a mass spectra here, and this shows the mass of the compound and how it can break apart. So all of these little fragments here are how the molecule breaks apart. This is the infrared spectra. This shows us the functional groups in here, and we'll learn briefly how to interpret some of these spectra. And the importance of this is great. After we run a reaction, we have to be able to identify the product so we know exactly what we made. So when a new compound is discovered, the structure has to be determined. So if it's an old compound, we can compare it to spectra that's already existing. But when you make a new one, we have to be able to figure out exactly what it is. So there's three methods of spectroscopy that we'll be looking at. One of them is mass spectrometry, which gives you the mass or the molecular weight of the compound. Infrared spectroscopy tells us about the functional groups. And nuclear magnetic resonance spectroscopy, or NMR, tells us about how it's connected together. So mass spectrometry measures the molecular weight of a compound, like we just mentioned. In order to obtain a mass spectrum, we have to have an ionization source, a mass analyzer, as well as a detector. This picture here shows our instrument lab, or the Cannabis Center for Excellence lab, where we have several different types of mass specs, and there's different types of ionization, and also different detectors. All of them in some form are going to give us a spectrum that looks like this, where we get a mass, or the M+. And these all are fragments. And that shows how the molecule breaks apart. The tallest peak is the base peak. And this M+ here, the mass of the compound, is also known as the parent peak. And each of these mass spectra are unique to each compound. It's kind of like a fingerprint for the compound. There's lots of ways to use mass spectrometry. One of them is to figure out drug metabolization. We can use it to characterize compounds. We can use it to quantify and qualify. We can determine how much and what pesticides are on different foods. We can use it to look at soil and groundwater contamination, any toxins that are present in fish fats, such as PAHs or PCBs. It's often used in forensic applications, and most recently in the laboratory that we have, it's being used to quantify THC, CBD, and CBN in hemp as well as in marijuana. So we can see different compounds here. These all have the same molecular formula of C6H10O. And you can also identify here that they all have different fragment patterns. Their parent peaks are the same, but they look different in each of these spectra. You will not be asked how to fragment these or even identify them. Just be aware that each compound has its own unique mass spectra. The next type of spectroscopy we'll be looking at is infrared spectroscopy. This measures the wavelengths in IR spectrum. We've seen this figure before in general chemistry, and we can see what's visible to the human eye. And then we have these other waves up here. Infrared is using infrared wavelengths, and it looks at how these wavelengths will bend and stretch molecules, and that changes depending on the functional group. So if you have greater polar differences between two atoms, there's bigger bending and stretching. So for example, bending and stretching between a CH versus an OH, this one will have greater stretching. And if you have greater stretching, it's going to have more of an effect. And there's all kinds of stretching that you can do. We have symmetric stretching. There's anti-symmetric stretching that kind of looks like scissors. There's in-plane bending and also out-of-plane bending. So you can see the different motions that you might encounter there with the infrared stretching and bending. There's a table that is used in order to figure out what each of these stretching and bending means. The functional groups will absorb at certain wavelengths and give different intensities that are very unique to each of the functional groups. For example, an alcohol has a very large stretch because H is very nonpolar and oxygen is very polar. H is not very electronegative while oxygen is electronegative. So this is a strong, broad stretch, and that absorbs at 3400. So we can know reliably that we're going to see alcohols in this region. So that's how this table is used. We find the different peaks on this table and we can relate them back to what functional group they are. Things that are between 3000 and 4000 are typically NHs, OHs, and CHs. We have triple bonds in the region between 2 and 3000, and then our double bonds show up between 1500, 2000, and then low 1500 is the fingerprint region. For each compound has its own unique fingerprint. It's difficult to interpret compounds based on just the fingerprint region because they can look similar sometimes. So if we look at this particular IR spectra, we said that between 3000 and 4000 are typically NH, OH, and CH. And if you go back to that table on slide 7, remember we brought up that OHs show up around 3400, which is about this here. And it's strong and broad. So strong is that it goes almost to the zero transmittance, and broad is that it's fat. So this is an OH stretch. These right here, just below 3000, and if we look at the table, things that are below 3000, that are just below 3000 are alkanes and alkane CHs. So that's at 2850 to 2960. These are alkane CHs. And then all this stuff here is in the fingerprint region, which we don't really have to interpret. So our main functional group here is an alcohol. If we now look at this one, I don't have any alcohols because there's no big broad peaks. I do have one here, which is about 3400. And if I look to my table at 3400, what else is in the 3400? I have this NH here. So this is an NH. These are below 3000, so these are the sp3 or alkane CHs. And then I have another peak here that's around 1700. That's just above the 1500 fingerprint region, and if you go back and look, this is some sort of carbonyl. So C double bond O typically shows up around 1700. If we were doing a reaction and we had two compounds we suspected could be the product, how could we use IR to distinguish these two? If we look at acetone versus 2-propanol, they have the same formula of C3H6, and acetone has this ketone here, so that's my functional group. 2-propanol has an alcohol and an alkene. So if we look at the table, I can figure out how to differentiate these. So an ketone has a peak at 1715. So that would be one that we would see for acetone. We'd also see the CH here. In the enol, there's an alcohol present. So we're going to see something at 3400. That one will also have the sp3. But because it's a carbon-carbon double bond, we may also see this alkene carbon just above 3000, and those would be the big differences there. So for the ketone, we might see a peak around 1715 wave numbers. And for the alcohol, we'll see that stretch, that broad stretch around 3400. And for the CH of the alkene, we're going to see a stretch around 3020. So that's how we would differentiate these two compounds.